dreaming, and they're controlling the dream. And they somehow ask these subjects saying that, well, once you're in lucid dream, trying to do X and Y and Z, like move your fingers, or trying to move your fingers in your dream. And they do this, and they do fMRI simultaneously. And they found that when they're dreaming and when they're trying to control their body parts, like moving their fingers, the corresponding brain area is activating too. So it appears that in dreams, everything is, your brain is responding quite similar to when you're awake, except that you're not, except the motor part is not functioning. Yeah.
So what does that say about consciousness then? If your kind of working definition of consciousness is that it's not dreaming, that it is some sort of awareness during wakefulness, I'm just curious how this study of dreaming neural activity being somewhat similar to conscious neural activity, how does that impact your questions about the nature of consciousness itself?
Well, I'm not sure if I get your questions, but I don't think they contradict to each other. I mean, dreaming, if you study dreaming and found that, well, the dreaming stage is very similar to awake stage, but without motor part of the area being activated, and that doesn't contradict with consciousness theory, right?
Yeah, maybe I'm misunderstanding then or misremembering your opening slide where you essentially equated consciousness with
experiences.
With experiences.
Yeah, but in dreaming, you definitely have experiences. So in my definition, you're conscious.
So dreaming is a state of consciousness as opposed. Okay, then I'm sorry. Then I misremembered. Okay, great, thanks.
Yes.
Okay, I'm sorry. I have a question about the role of approximation in perception. So you had started with a picture of the ball coming towards the baseball guy and the baseball guy trying to hit it. Now, I've noticed that compared to computers, and I'm originally from computer science, compared to computers, the way the brain makes inferences, predictions, is very approximate in nature compared to a computer. For example, if a computer sees a baseball coming at you, it makes exact calculations as to what the trajectory is, where it is going to go. On the other hand, the brain does it in a very approximate way. What is the benefit of this kind of approximation? Does it make the calculations quicker, more versatile? What does this approximation buy us?
How long do you have? That's a terrific question. So I'm going to broaden it by saying that there are a great many people who have observed that our behavior is in many ways close to optimal. And that means that we do things in the best possible way, make the best possible estimates. And I think that's how the computers are doing it. They're doing it in an optimal way. But the way the inference they've made from that is that the brain also behaves as an optimal device. And I think that's a reasonable intuition, except I don't think the brain is trying to optimize its actual performance. I think the brain is trying to optimize some other considerations that are really critical. I think it's trying to optimize brain size, right? I think it's trying to do things in ways that minimize the amount of brain tissue and especially minimize the amount of wire that's needed. The downside of allowing the brain to increase its size to do things optimally would be, of course, that we might end up with heads that are so large that we can't move around. And I think it's trying to optimize energetics. The brain consumes quite a lot of energy, and the calculations I've seen on how much energy it takes and how many action potentials it can get out of that energy are really impressive. It's on the order of a half an action potential per neuron per second is what you can get for the energy the brain uses. And I think it's probably trying to optimize its use of energy because it probably can't afford to increase that tenfold. So it's adopting solutions that are approximations, and as far as the brain is concerned, good enough is good enough. And I think that's how the brain works. I think that's how it's designed.
Other questions? Yes. Sorry, first I want to ask Professor Lisberger that just now you're talking about the motion control. So like baseball, you have a fixed target, which is a baseball. Now I also recall yesterday Professor Lim talked about improvising the music. These things, how, let's say when we doing improvising, when we're playing an instrument, there is no fixed target for it to hit. We don't have a fixed pitch to hit, but what we want to do is we want to be congruent with what we played before, and we want to stay in the whole structure. So does that have different types of perception, or is it the same types of perception?
That's a hard question. My personal experience, when I was a boy, I was an acceptable pianist, but I could not improvise if the world depended on it. And my interpretation of that is that inside of my brain, I'm not capable of creating the targets. And so what I think is happening, what I think the difference is that in the kinds of tasks I'm talking about, the targets are explicit and they create activity, patterns of activity that we can measure and quantify because we're controlling the stimulus. And I imagine, and I have emphasized the word imagine, that when someone is improvising, they're generating those targets inside their brain, and it may well be the case that they're actually generating activity in some of the same places that the activity would occur if they were hearing those sounds that they're about to generate. So I think it's internally generated targets versus externally generated targets. But my imagination is that the downstream consequences for the actual sensation to action plan are very, very similar.
Okay. So does it does it involve any computing powers of the brain, like when a baseball, actually when you go to catch the ball, you hit the ball, it doesn't really need you to think about too much, because if you think you miss it, then what about when you're improvising? At least if from my experience, and I heard from other musicians, is that they don't really think about how to improvise, because if you think, then you're likely to miss the hit.
I don't know. Do you have something to say about this, Brown? We're almost at the boundary between conscious, unconscious, and preconscious behavior. And what I'm saying is that they're really all the same. It's just a question of where the stimulus or the behavior comes from. And I'm saying that for improvisation, I'm guessing that the consequences of sensory events are in your brain, and you're responding to them. And for the kinds of activities that I talked about, the consequences of sensory events come from outside, and you respond to them.
We're about a half hour behind, and we don't want to miss the chance for more networking and pursuing questions over lunch. Anyone have one last question? Yes. You want to get the mic?
Test. Hi. I actually have many questions, but I'll stick to the simplest one I have. I was actually quite surprised that mirror neurons did not come up during the both talks. So could you tell us a bit more about how consciousness and understanding what happens around us is linked to the mirror neurons that we have?
Okay, mirror neurons. I think at this stage, in my part of the talk, I'm talking about experiences. I'm more focused, when I talk about consciousness, it's more focusing on these qualitative sensations or experiences and what happens in the brain when you have experiences or no experiences, and which is not at the level of mirror neuron, which probably talk about how you reflect other people's behaviors or even, so I'm not talking about anything that's higher level or like metacognition or self-awareness and stuff like this. So at this stage, they are not linked that closely yet.
Anything to add to that?
Nothing tangible.
Your opinion of mirror neurons?
My opinion of mirror neurons? My imagination of mirror neurons is that they are at the boundary between internally and externally generated actions. And I could easily imagine that mirror neurons might be involved in improvisation, for example.
Okay, let's thank both speakers and have some lunch.
Hi everyone, there is lunch upstairs, and the next session will start at 2:15, so please be back in the hall by that time. Thank you.